Okay, so in today's class, we will be continuing the rest of the solution, the rest of the class, the rest of the previous week lesson. So we will be continuing the calculations that we have done. So we were doing shunt stub matching. So we have come to the stage where we have designed the distances to the stub. So the distances to the stub we have uh, decided as V1. We have got the distance by taking the difference from the load point up to the uh, uh, location where we had the intersection between the SWR circle and the unit circle. So we have got this output, and for D2 we have got 0.325 minus 0.65. 0.065. No? Okay, so these points were the intersecting points. Intersecting points that we obtained by taking the intersection between the SWR circle and the unit circle. Okay, so SWR circle of the load point. Load point. So we have taken the difference and we have found the distance that we need to define as the point of, as the distance to the stub. Do you have questions? D2 is hard. What is the value for D1? 0.0774. Like this value is different. 0.176. Okay, so you got the intersection point. So how did you? What is the value of the? Wavelength to that intersecting point, the first intersecting. All right. So after deciding the distance values, we need to choose the distance value we require for our design. So we cannot use both these distances. Both the distances we cannot use. We are only going to design one stub. So therefore, we need to decide one of these two values. So we need to decide one of the distance values out of D1 and D2. So usually we take the one which is closest to the load. So so usually we design the stub such that it is close to the load as much as possible. Do you have any questions? So the main reasons are like to improve the bandwidth, improve or retain the bandwidth, and reduce the losses, reduce the power losses. Okay, so far we have decided at what location we need to place the stub. Okay, so but there's one more calculation that needs to be done. So the next calculation that we need to do is we need to decide the length of the stub. We need to decide the length of the stub. So we have decided the distance to the stub from the load. Okay, so this distance we have decided. But now we need to decide the length of the stub. The length of the stub we need to decide. So that we need to decide based on the admittance that we see here. Okay, so we observe some admittance at this intersection point. So based on that admittance value, we need to decide the L value or the length. Okay, so based on this, we decide the 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 length. Okay, so the length we decide based on the admittance value. Okay, so the admittance value that we get in these intersecting points, we need to first decide. Okay, so I will erase this part. At the intersecting points, the admittance values you need to decide. Okay, based on your calculations, you can find out the intersecting points impedance. Okay, so I will go ahead with the values I have. Okay, so you can decide, I mean, you can use your speed chart and your calculations, and you can decide the intersecting points admittance values based on that. Okay, so what you need to do is just find the value of the admittance in here. So since we are considering the admittance in here, in this place also, you will be measuring the admittance. Okay, so this place we will say y1, and the next intersecting point we will take as y2. So the admittance value that you find using the Smith chart for this point will be the value that you just measure from the circles. Okay, so this entire chart you consider as admittance chart in this whole calculation. Okay, so you don't have to get confused whether this is the impedance value. Like sometimes you will think this is the impedance value, but since we have started with the admittance value, the the extension of that admittance value is also another admittance value. So uh, after we have decided the admittance value for the load, we are continuing all the calculations in terms of admittance. Okay, so this places admittance value and the second intersecting points admittance value we can find by taking the value of the intersecting point in the Smith chart. Okay, so can you find the intersecting points, the values of the intersecting points? Okay, so I think you will get some different values, right? Now, also, I just want to show you that like actually I'm following the examples that are there in the book. Okay, so uh, okay, so you can carry on with your calculations. In the meantime, like I'm showing that I'm referring the example sums in this book that I have provided you as the reference book. In that book, we have two examples, shunt stub matching and series stub matching. Okay, so that example only I'm following. Okay, so the values that I have given you are exactly those values, right? So you can check in the book also whether like your values are actually matching with the values that are coming from this book's values. Okay, so these values that I have, given you are those values, right? So this 0.176, according to this book, it has come like that. Okay, so you need to decide whether this point that you have selected is exactly the point that has come in the book. This like value is like point something, between 0.06 and 0.07. Okay, so that value you need to just check again whether it's like overlapping with your answers. Okay, so you can verify with these values. Okay, so I'm just like focusing on the method that you need to follow once you are solving this kind of a question. Okay, so this is the question example that we are following. Okay, so after we decide the values of these intersecting points like admittance, next comes the point where we need to um, give the next solution. The next solution is the length of the stub. So in order for us to get that length, what we want to do here is that we want to like convert this admittance value to a real value. We want to obtain a real value, for the uh, real value for the as the final uh, as the for the final real value for the final admittance of the system, for the final admittance of the system. Of the system. So what do I mean by that? So the value y1 is 1.00 plus j 1.47, right? I want to convert this into a real value. So in order for me to convert this into a real value, what should I do? Now it has both a real value and imaginary value, right? So I want to create a real value out of this. So the imaginary value should be what? I should try to cancel it. I should try to cancel this, right? I should cancel it out, and I should try to make it 0, right? In order to make it 0, I need to add how much? I need to add how much of impedance? I need to add now how much should I add? If I'm adding some impedance or admittance in this case, how much of admittance should I add to this? Right? In order for me to get the final admittance as 1.0, then y1 plus how much should I add here? This should be 1.0. That's all. Is it difficult? It's just mathematics, right? 1.47 plus, I need to add something, and it should give 1.00. What is the value I should add here? Minus 1.47, right? This is the admittance value I need to add, right? So in order to add that, the thing I need to do is that I need to find like the place where I can find minus j 1.40. Okay, so now we have already come to this point. We have come to this distance point. After that, in order to cancel the admittance in that part, we are adding some additional thing with minus 1.4047 into this design. Okay, so I will just first indicate that somewhere in here. So we will get the admittance of minus values in the bottom part of the Smith chart. Somewhere along these lines, we will find this point 1.47. Somewhere along this line, we will find it. So I will mark it in here as the minus 1.47. Okay. So once you decide that minus 1.47, then we can by adding this stub with this length, we can cancel out the imaginary value that we got for the admittance in the y1 point. Y1 point we have obtained once we go to in the transmission line. Once we start from the load and once we go a distance of V1 up to this stop point, we have the impedance of this value. Okay, so in order to cancel out this, we are adding this additional stub with minus 1.47 of susceptance, we call it. I mean admittance, minus 1.47 admittance by creating a stub of length that is suitable for that, and its admittance is minus 1.47. Okay, so the length of that stub is coming from the distance that we measure from the from the short circuit to open circuit point in the Smith chart. Okay, so that is another point. Okay, so we decide like whether this is short circuit or open circuit. So based on the circuit condition at the end of the stub, we need to decide at which point in the Smith chart we need to measure the distance to this intersecting point. Right? So in admittance chart, we will be getting the short circuit in this position. So because of that, the length of the stub will be measured as the distance from the short circuit point up to this intersecting point. Okay, so I will, it's hard for me to write all this in this diagram. I will try to draw another one. So I hope it is actually a lot of facts together. So first you had some kind of a intersecting point related to the distance to the stub. Okay, so when moving from, I think, okay, so this is the unit circle. So the 0 must be here. 1.0 is here. So from there we have the load point. Load point, we moved up to the unit circle point, and then unit circle has a certain impedance value. So unit circle has a certain admittance value of J 1.47. So that in admittance value we are trying to cancel now by adding a similar like admittance value at the bottom of the Smith chart. So we are finding that admittance value, which is somewhere along a line in this Smith chart, and you can find the admittance values intersecting point. It could be somewhere around in this line. It doesn't necessarily need to be in the unit circle. It can be somewhere along this line in this bottom part of the Smith chart. So you can find exactly where minus J 1.47 line is in. Okay, so it is along this line. So once you have found that value, you can find the distance to that point from the place where we have the short circuit in the chart. Okay, so we need to find the distance from the short circuit point to this intersecting point. Okay, so we are assuming that we are doing a short circuit stub. So if you are doing a short circuit stub, then the distance from that short circuit stub to this point in the transmission line is what we are trying to find. So this is the short circuit point. And from that point up to this point, we are trying to find the distance. So this length we are getting as this length from the Smith chart. Okay, so first I asked you to find this impedance admittance minus 1.47 line. So can you spot that? Minus 1.47 line. Is there any problem related to that? Do you find 1.47 line? No, actually, you don't have to take the intersection between unit circle and that line. You just have to draw the line up to the scale in the bottom, right? You just need to find the intersecting point in the bottom scale. Can I order clear now? Okay, so the shunt stub matching in shunt stub matching, you finally need to decide the 1.47, the line which correspond to minus j 1.47. You don't need to do any intersection with the unit circle. Okay, so the point of this line, the point of this drawing is to just find the distance from the short circuit to this intersecting point. Okay, so we are not going to find any impedance value along this line. So therefore, we just need to find the distance, length from the short circuit point from the to the intersecting point. Okay, so we need to keep in mind that this is the short circuit point in the admittance chart. Okay, so the open circuit point is here in the admittance chart. Okay, so those factors you need to keep in your mind, right? So after that, you have actually done the calculation for the first solution. Okay, so like you have actually we have decided this length L1 based on the admittance Y1. For the admittance Y2, we need to decide the length for the Y1, Y2. Okay, we need to decide the length for the Y2. So that we need to do separately. Okay, so how much of admittance we need to add in that situation? If we take Y2 admittance, if we go with the Y2, then we need to add how much of admittance? We need to add plus 1.47, right? So if we are adding plus 1.47, what is the length from from the short circuit to the point? What is the length? How can we, right? So I mean, in that case, we have to find the line which correspond to plus 1.47 in the Smith chart, which is on the top half of the Smith chart. So we need to correctly find the line, and we need to find the position of its intersection on this outer circle of the Smith chart. And then since we are finding the short circuit length, okay, from the short circuit point, the length to that point, we need to keep in mind now that we are trying to find the length from the short circuit towards the stub, right? So in that case, we consider that the short circuit point is like a load. So from this point only, we need to measure the distance. Okay, so not like we don't take the distance, the shortest distance. We always follow a certain direction. So we since we are measuring from the short circuit point up to the load point, I mean, up to this intersecting point, we have to measure along this direction. Okay, so you will ask, like, why are we going in this direction? You will ask. Now, in the Smith chart, it is given that the towards generator, right? This direction as towards generator in this direction. The arrow is given in this direction for towards generator. So towards some kind of a load or towards some kind of a input value, you need to the direction is along this direction. Okay, so uh, since we are considering the transmission line, uh, transmission line transmission line when we draw the transmission line, our like short circuit happens in here. So this is like the kind of input side. This is like the input side. So this is like the load point, right? We need to consider that this is like the load point, and from there we need to move towards the input side. So we need to move towards the generator, and therefore we need to go in the anti-clockwise direction towards the intersecting point. So therefore, like once we get the L value, it will be higher than L1. L2 value will be higher than L1 value. So another L2 value will be obtained for the Y2 admittance and its solution. Okay, so based on that, you will get another set of solutions for the second stub solution, second stub, I mean calculation. Okay, so we will get uh, so I will write down what we have discussed. So the first solution, the first tuning solution will require a stub with uh, with admittance value of minus J 1.47. Okay, so since this is only containing imaginary value, we actually consider this as susceptance. Okay, so susceptance is coming once you take the inverse inverse of a impedance value. If the impedance value is a capacitance. So anyway, this admittance value, if it is not having the real value, we are considering this as a susceptance of uh, uh, the load, the susceptance value. So once we are considering admittance value, we have susceptance and we have conductance, right? Admittance value is given as susceptance and conductance. I think as I remember. Okay, so we can actually denote this using notations, right? So this is not. Uh, I think I will. So the admittance value consists of conductance and susceptance. So the real part we call as conductance, imaginary part we call as susceptance. The length of the do you have any question? Do you have any question? The length of the short circuit stub that gives this susceptance can be found by moving from uh, y equals y reaches infinity. Okay, so this place is actually y it reaches infinity. The main reason is z equals 0 in there. So y equals 1 over z, right? So y reaches infinity there. So from reaches infinity point and moving along the outer edge of the chart towards the generator. To the intersecting point of minus 1.47 J and um, the outer circle of the Smith chart. And boundary circle of the Smith chart. So the boundary circle is this. So the intersection between the boundary of the Smith chart and the line we take, and we find the distance from the intersecting point towards the with the short circuit point. So this will complete the design. So the stub length that we will get, uh, will be 0.095 lambda. And similarly for the second solutions, we will get 0.405 lambda. Okay, so based on the solution that you select, you can select a set of solutions D1, Y1, L1, right? So based on your solution, you can select your set of solutions, right? So like you can either select D1, L1. This is one solution you will select. One solution or solution one. You can select this one, or you can select the next set that you obtain D2, L2, right? So you can select either of these two values, okay? So you can either select this or this one. Is it okay if I erase this? I write it. Is it okay if I erase this one? So the important thing you need to keep in your idea is that the Smith charts, the location of the short circuits and the open circuits in the admittance and the uh, impedance Smith charts. So in admittance Smith chart, you will have Z equals 0 here. Z reaches infinity here, right? Z reaches infinity here, then Z reaches 0 here. So this is open circuit and this is short circuit. So in the admittance, this is the impedance chart, right? So this is the impedance chart. So once you take the admittance chart, admittance will be in here. Based on this situation, it will be 0, right? Admittance 0 and admittance will be infinity over here. So in the admittance chart, in here we will have the short circuit situation. In here we will have the open circuit situation. So in impedance chart, in here we will have open circuit situation and we will have short circuit in here. So those things you can actually keep in your mind, and the unit circle is here, somewhere here, unit circle. So it will have actually my drawing is not good. Okay, so the unit circle is actually extending up to a radius of 1 from the starting point. Okay, so this is the unit circle 1 plus 1j. So this is the unit circle. So those things you can remember regarding the Smith chart when you are solving this equation. So solving these problems. Another thing is that you can actually find the solutions for other scenarios like series stub matching. So the second problem is series stub matching. So series stub matching is also doing the same thing. I mean, is also following the same set of procedures, same set of procedures, series stub matching. Okay, so series stub matching will normalize the impedance and do that part. This is as similar as before, but in here the main difference is we are going to consider the Smith chart as an impedance chart. Consider the Smith chart as an impedance chart. We will be working with impedances in here. So impedance means we are going to consider Z values. Z values. Okay. So the reason is because we want to add the series impedance to the load impedance. Okay. So once we are designing this circuit, we are going to be left with a circuit like this, right? So we are going to add our stub to the transmission line like this. Okay, so we are having a certain load. The load is connected in series with this stub. So this stub has a certain impedance. Right? So it has a certain impedance and the load has a certain impedance. And in order for us to match these two circuits, the stub-based transmission line and the load, we need to add these two. So once we add these two, the final value must be a real value in order for it to be a matched circuit, right? So therefore, we need to consider impedance chart. And we need to find the values of the impedance of the stub, and we need to cancel out its imaginary part. So once we are doing the cancelling, we will be able to find the stub length and the distance to the stub. So in here also we are going to decide the distance to the stub and the length of the stub. So the width of the stub that will be decided using another like calculation. Okay, so I will discuss about the series stub in the next class. So is it possible for us to do the next class tomorrow? Is it possible for